So, page 32, find the area of the region bounded by y equals the ln of x, the ln of x, ln of x, the x and y axes, and y equals 3. All right, so let's get that information in here. ln of x, I put it in y2, but that's fine. All right, x and y axes I'll need to have. I'll do a quick zoom 6, see where we're living. All right, if it's bounded by the x and y axes, x and y axes, it looks like we're talking about this little region right here. All right, so if I want that area, it looks like it kind of makes sense, if I have a choice in the matter, to integrate with respect to y rather than x, but they're having us do it both ways. So I'm going to change my window so that it mins out for x at 0, and maybe just like actually I'll make it a smidge below 0. So negative like 0.1, just so I can see the axis. I don't know that I need to go to 10 for y. Let me go to like 5. That looks fine. All right. So if I'm doing this with respect to x, the first thing I notice is I have a little rectangular region here. So I'm gonna take care of that with good old geometry. All right, I'll draw a quick sketch though. All right, so looking at something like this. So you could actually, if you wanted to, use rectangles to get a good chunk of this, and then go the rest of the way. I mean, if you want, you can find the area of this and then work the other way using the technique that we covered on the previous page. But now actually that I'm looking at it, the more I look at it, the more I want to kind of go in a different direction. And that is to say, why not take the area of the entire figure, subtract from it the pieces that I don't want, in this case the piece that I don't want, which is this region here. I'm just putting in some Riemann rectangles just to really show that I can get from beginning to end of this region without any gaps along the way. All right, so this is going to be some value y, because again, from the x-axis to some point in space, we're looking at y. Alright, the thickness is dx, so if I want the area of that region, I would just need to know where I'm starting and where I'm stopping, and I would be multiplying y times dx. Alright, now that y is given as the natural log of x, so I got my ln of x dx. I just need to know the beginning and the end. All right, it's pretty clear that it's beginning at 1, all right, and that's, you know, as an x-intercept, natural log function does begin at 1 because natural log of 1 is equal to 0, so we're good there. All right, we only want it to go out as far as y equals 3, or up as far as y equals 3. All right, so it's bounded by the x and y axes, y equals 3, and the natural log of x. Alright, so it looks like we have to somehow figure out where this thing is going to max out. And I guess the only way to do that would be to see where they eventually intersect. So I could do that a couple of ways. Let me make my x max a little bigger. It looks like we have an intersection here. Second trace 5. Enter, enter, enter. It's about 20 and change. So if I continue this trend, that kind of made it look too level there. I'm going to have an intersection here at 20.08-ish. This is a 0.8. All right, but that's what you would get if you took ln of x and set it equal to 3. All right, so that's the same as saying log base e of x is equal to 3. So x would be equal to e to the third. All right, just quick verification. E to the third power, yeah, that's about 20 and change, so that's where we're going to max out. All right, so the rectangle that we want actually is going to be much further down the line than I had initially thought. It's going to be over here. All right, so all of this is going to be part of the action here. All right, and so the length of that entire rectangle in terms of x is e to the third power. The height is 3. So 3e to the third power minus that integral will get us where we need to go. All right, so 3e to the third power minus math 9. It's pretty easy to just type it right in. ln of x, close it up, and then pop in an x, and we're looking at about 19.0855. Alright, so we're going to look to see if there might be an easier way to do this. If we want to tackle it with Desmos, and clear out this stuff, we have, I'll go with f of x immediately this time rather than changing it after the fact. ln of x equals, f of x equals ln of x, and then y equals 3. Fix my zoom. Here you can see it's pretty more readily apparent that there is an intersection. All right, and if you click on it, you see where that intersection is. All right, so that's pretty nice. All right, now you'd still have to do some of this background work, like solving for the value of x, but you have the nice diagram that kind of points in the right direction from the word go. All right, so that's kind of really the benefit of Desmos. All right, so let's take a look at it from the y perspective. So looking at it from y, I think it's pretty easy to see that the entire region is bounded by the function, right, and the y-axis. All right, I think what I'll do here is a quick snip, and I'll bring it in. So what I would do is take a snip of this and then rotate it and reflect it. All right, so I kind of did that off screen here. And so this is what you would get if you were to, well, actually it's, this one is the one that you would get if you rotated it. So I'll just move this one aside. All right, so so we started off with this, right? So then rotate it and you get this, but your x values are pointing in the wrong direction. The positive x's are on the right, the negative ones are on the left. All right, so if you reflect it, it brings you this, which is scaled appropriately. All right, so we have -1, -2. Actually, this I believe is scaled because this is supposed to be 3. So this has got to be 1, 2. So every box is worth 2 units. All right. So we have our intersection up here somewhere. We know that from previous work is e to the third. And in fact, I'll write that as a coordinate 3, e to the third. All right. So this is my y-axis and this is my x-axis. So it gives you a little bit of a better perspective on it because you can see here that it's pretty I don't want to say obvious, but it's a little bit more obvious anyway. that the rectangles oriented this way would span the distance from the lower bound to the upper bound. Okay, that was pretty awful. And so maybe I'll just get one more in there. Even better. Look at that. Jeez. So each one of these horizontal distances, normally they'd be dx, but I changed the orientation, so these are going to each be dy. All right. Normally the distance in space from the x-axis up would be represented by y, but now it's from the y-axis to a point in space. So that distance is now x. All right, so it's an inverse relationship. All right, so I'd be looking at over the interval, because again it's bounded by the x and y axis. Oh, that's a little on the thick side. So bounded by 0 and 3 on the y-axis, we're looking for x dy. And x, well, we have an equation y equals ln of x. Well, I need an x equation. All right, so y is equal to log base e of x. Natural log is the same as log base e, which means that x, if you convert it into exponential form, is going to be e to the y. So over the interval of 0 to 3, we have e to the y dy. The antiderivative of e to the y with respect to y is e to the y from 0 to 3. So e to the third minus e to the 0th. So e to the third minus anything to the 0th power is 1. So e to the third minus a 1 is going to give us that 19 and change that we got before. So 19.0855. All right. So in both cases, we're not given units, so we would say units squared. All right, but it's pretty clear that one way was a little bit easier to do than the other. All right. Now, oh, that's not what I wanted to do. Okay, I can actually pull it in from here. Oh, not that. This one. All right, but I wanted to show you very quickly how you can pull it directly from the graph itself without rotating it. All right, so the idea here is to look at the bounded region. All right, so that bounded region is spanning from, again, 0 to 3. You'd have some arbitrary rectangle living in that interval that we would have, or we would give a thickness of dy. Any point in space has x. I just dropped something, apologies. An x component and a y component, so that x component is the horizontal distance from the y-axis, the y component is the vertical distance from the x-axis. So to get from this location to this one, I'd have to go x units. All right, so it's still going to give you the same setup, just without having to do the whole rotation thing. All right, because if you're looking at it like, wow, how am I supposed to do all this without the app that you use to rotate everything? Well, you don't necessarily need to. Right? Or you can get the app. The app's cool. Okay. It's not the app that's expensive, it's the devices that you need to use the app that's expensive. Now, if you were to do this on Desmos, you would first, I mean, we have our function in there. You would first want to write the function in terms of y, so g of y would be equal to e raised to the y power. We did all that work on the side. I quickly verified that it's the same. All right, we're looking pretty good there. So then anti-differentiate over the interval of 0 to 3. my g function, which is g of y again, dy, and that would spit out the value for you. Number 3. On the area of the region in quadrant 1, bounded by x squared plus y squared equals 8, x equals 1/2 y squared, and y equals 0. Alright, so it's definitely quadrant 1, so we got that going for us. This equation we can solve in a couple of ways. One way would be to solve it for x, in which case you'd have x is equal to 8 minus y squared under a root, slap a plus or minus on that. Just going to move that over. Or we could solve it for y. Same idea, just swapping the x with y's. All right. The second equation is solved for x in terms of y, but we could easily solve that for y in terms of x if we wanted to. You know, double both sides, so we'd have y squared is equal to 2x, and then root it plus or minus the square root of 2x. Do I need to do that? Probably. I mean, I see with respect to x, with respect to y, so it kind of makes sense. All right. So now in terms of the diagram, you go to the calculator, you go to Desmos, it's up to you. Let me do it like I've been doing it. Put it in Desmos, or the calculator first, then we'll go to Desmos. So the square root of 8 minus x squared, then negative that. So I'm going to use a little nifty shortcut, negative, and then alpha trace y1. So the negative of my equation in y1. All right. X is equal to 1/2 y squared. Can't graph that in the graphing calculator, but I can graph y is equal to the square root of 2x. And I could also negate that, so negative y3, alpha trace y3. All right. I can make some of it bold and some of it not, so it's easy to distinguish one set from another. All right, and then we see what we're up against here. All right, so we got a circle, or at least something circular, and something that appears to be a sideways parabola. All right, so we only want the region in quadrant 1. All right, so all these bottom halves can go. All right, so the left half here and the bottom half here. So let's first get rid of the bottom halves. That's actually the negative stuff. So let's start with that. And then if I only want the part in quadrant 1, what I can do is just restrict my domain. So instead of going from -10 to 10, I go from 0 to, I don't even need to go to 10, maybe 0 to 5 for x and y. So 0 to 5, 0 to 5. Take a look, not too bad. Maybe I'll give myself a little wiggle room, -0.1, just so I can see the axes. All right. It doesn't quite make the connection there, but that's a calculator issue. It's just incapable. All right, because it thinks it's going vertical when it's really not. All right. So this equation, x squared plus y squared equals 8, is really a circle with the center at 0, 0, and a radius equal to the square root of 8, or 2 radical 2 if you want. All right, so we know the extreme values here on the axes. And again, I'll just do what I've been doing, draw a quick sketch. All right, and then, you know, the other part is circular, so I'll try to make that look somewhat circular. I mean, best I can do, even with the line draw tool, or the geometry tool. So this is my y equals the square root of 2x, also known as x equals y squared, oh, sorry, 1/2 y squared. And this one I'm just going to write as x squared plus y squared is equal to 8, at least for now. All right. Now, so I want the region in quadrant 1 bounded by the circle, the sideways parabola, and y equals 0, also known as the x-axis. All right. So this is really what we're after. Now, if we look at it carefully, we see that there is a little bit of a line of demarcation here, because the first part is bounded between the x-axis and the function y equals the square root of 2x. All right, so we have a y here, we have a dx, but that y is going to be different from the y that we have here. I hate when that happens. You know what I'm going to do? I'm going to do this. So I got my dx here, that's consistent, but this y is going to be a different y. All right, it's going to be associated with this equation, and this y will be associated with this equation. All right, we need some bounds. That's going to be related to the intersection. So let me get to that intersection there. A nice clean 2. That's something. 2 comma 2. So we know that this is going to be a 2 here, and this is going to be a 2 here. All right. So if I go from 0 to 2, I'm going to have a y dx, but for the red stuff. Then I can add to that the integral on the interval of 2 to, this is 2 radical 2, you know, radical 8, 2 radical 2. We're going to have another y dx, but this time related to the purple stuff. There's some soda, there's some purple stuff. I love the Sunny D. Alright, so 0 to 2. The y equation for this part is the square root of 2x. We got our dx plus 2 to 2 rad 2. The y here, we talked about this previously, is the same as the square root of 8 minus x squared. So we just have to get the solution to these integrals, add them together, and we'll have it. Now before we do that, I kind of want to do this with respect to y and see what we get there, because maybe I'll just steal that answer. You know, because it's just computation. They should end up being the same. Alright? So with respect to y, let me just get rid of some of this fluff in the middle here. I hit copy when I meant delete. I got some of these labels that I suppose I could leave, but some of them have to go. Overshot the Mac. Alright, let me bring this down, clear that, bring it back up. Alright. Alright, so what I want to do is go over the interval of 0 to 2. I'm going to go with a nice brilliant blue here. Over the interval of 0 to 2, I'm going to create rectangles within this bounded region. We just need to know that those rectangles are representing the difference between the two functions. Alright, because we have a y, I think I went purple before. We have a y here, that's the circle. We'll call that y1 for example. And then we have another y. Oh, what am I saying? Y? I mean x. Apologies. Call that x1. And then we have another x here that I'll call x2. If I do x1 minus x2, then I get the length of that rectangle. Its thickness, I'm going to do a little dash. Its thickness is going to be dy. That's why I had y on the brain. So, over the interval of 0 to 2, I need an x1 minus x2 dy. So that x1 is equal to the square root of 8 minus y squared. And the x2, that's the sideways parabola, that's 1/2 y squared.
All right, so the way it's kind of shaken out here, it's not going to be pretty no matter how you slice it. All right, but, oh, slicing is a different topic. So y1 and y3 have what we need for the first part of this problem, so that's what I'll use. All right, so I had hoped to be able to use the second part to kind of make things easy on myself, but it's looking like there's no way this is ever going to be easy. So y3 is where I have my rad2x stored, so I'll just pop that in there. So alpha trace y3, pop in an x, and then add to that math 9. Integral over the interval of 2 to 2 rad 2, or rad 8, because it's just less typing. And that would be alpha trace y1. And we get a non-real answer. All right, where did I screw up? Oh, 2 rad. So when I was like, you can write rad 8 instead of 2 radical 2, I zigged when I should have zagged. Ay, ay, ay. Ay, 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 ay. So 3.808 approximately. .808 square units. All right. So now the other way, you know, it's just more typing. I could just type it in, but I'll do this one with Desmos, right? Because it's inverted, so why not? You know, Desmos can handle inversions, so let's let it handle inversions. You know, so x is equal to the square root of 8 minus y squared. Good there. Then we add x is equal to 1/2 y squared. All right, so we're good to go there. So, well, we don't need the bottom half. We could restrict it, but first thing was first. We needed to get that intersection, which is 2, 2. All right, so we're good in that regard. All right, so now what I want to do is integrate over the interval of 0 to 2. And that was, well, we used x's here, so it's going to get confused. So let's do f of y and g of y. All right, so same graphs, so we're good there. And so f of y comes first, minus a g of y, dy, 3.808, so we're good. All right. So, yeah, the differences, it's a little quirky because, well, not quirky, Desmos is beautiful. The differences between the graphing calculator and Desmos is where the quirk comes into play, because you have the plus or minus for the equation that we put into the graphing calculator. The positive gives you the top half, the negative gives you the bottom half. When it comes to the inversion, the positive gives you the right half, the negative gives you the left half. It's something you just got to be mindful of, because a lot of people aren't used to seeing that because they're so used to working with the TI calculators, which doesn't handle inverse relations very well. So just something to be careful about. Just yet another thing to be careful about.